Hello, Professor.
Hello, Kumin. I'm sorry, really sorry. Today is so slow.
No, it's okay. It's okay. No problem.
Yeah, my computer waits like half an hour to boot up, so I'm sitting here just waiting for it to start. Sorry, that's a problem for Windows. Okay, any questions so far?
No, it's okay. It's okay. Yeah,
Okay,
I just got late in my assignment, but I'm gonna finish during this week. Yeah.
okay. But you see, I tried many ways to log in, so let me close this different one. Okay, so last week we go over the syllabus, and today, if there's no question, then what I'll do is I'll go over the basic manipulation of the linear algebra and also the whatever important to our course for the modeling, planning, and control for the Python programming. Okay.
Okay.
So, okay, let me bring up the slides. Okay. So first chapter is just like actually introduction, right? So next one, what's important is the kinematic diagram and the representation of the orientation. Okay, so let me see. The most important part for the modeling of a robot is its control. So a robot, okay, a robot arm, you do have a robot arm, right? And may have a tractor, whatever. So we try to model a robot. Basically, you robot, it's an actuator and the robot arm. That's one control loop. Okay. The other one is your vision. You build up your environment model. Okay. So there's an environment model you need to work out. Okay. There's an environment model. Second, there's a robot arm control. Third one, you also had this instructor, so you need to know how to do motion control. Okay, these are three topics usually need for a robot to control. Okay, to build up the environment to avoid. So what is first one, environmental model? Environmental model is like, okay, let's assume that we do have a drone, okay, or a autopiloting car or something, right? So you depend on a virtual model that you're driving on. So basically, okay, basically one thing is that you based on basic map system. So maybe the drone or the car, autopilot car already has some sort of map built by GPS or something. Okay, that's a pre-built map, right? But when you drive your car on the road, you drive your car on the road, you have to update whatever you sense nearby, right? So these two combined together, you build up a map model, okay? And then computer use AI to choose which route you should go, right? So that's actually the number one, environmental sensing, okay? You need to be able to sense where there may be a bump, there is a car or there is something obstructing your planned route, right? Then you need to make adjustment for it. So that is how you sense and build the environment model. So this is one model you need to build, okay? Second, robot arm. So let's assume that we are using a application of playing the chess by the robot, right? the robot will pick up some stone or some rook or whatever key, and then press on certain location. So that actually also depends on the sensing of the gimbal. Go back to do computation and then make a move, deciding which move to where. Okay, so that actually also is a feedback loop. Okay, and then your motion. Okay, is auto piloting tank. Okay, that's the same. We have a auto piloting tank. Right? There must be some sort of sensor you don't know, hidden, trying to sense that where it is. How am I going to adjust my motion controller to adjust my car to go to where? Okay, so these are different motion control system that or robot arm movement system that we need to do. So number one, you need to be able to come up with a mathematical model for it. So mathematical model, this one including the map, the environment, and also your own robot arm model. Okay, so the most important part of the first few chapters, we are actually learning the modeling of the robot arm. Okay, you will see a lot of homework actually. Just focus on the modeling of the robot arm from a mathematical point of view. Okay, and then that's the most important part. So before we go into those robot arm, you need to learn a few things. Number one, linear algebra is for sure. Operation of the array and the matrix. Okay. Second, you need to know about how to apply linear algebra. Okay, multivariable calculus. And vector theory into the robot arm and motion modeling. Okay, so these are the purpose of learning this different theory and then apply to that. Okay, so okay, I have a whole video on algebra in the course shell, so everybody can look at it. So I'm not going to repeat that portion. I'm going to today, because we have limited time, so I am going to focus on the motivation. Okay, the motivation of why we need to focus on how we actually would do this rotation and everything. Okay, so let's look at how we would rely on this linear algebra and multivariable calculation to solve the problem. First thing, let's look at the transform theory. Okay, transform theory. How the kind of transform we look at is actually translational. Okay. Second, it actually is rotation. Third one can be mirror. Flip-flop. Okay. But because we are using rigid system, so the robot seldom do the mirror and flip-flop. Mirror and flip-flop usually in the game theory, when you design game, that you need that. So basically, the kind of math we are learning right now can also be applied to 3D game design. Okay, but game is also modeling of some virtual reality. So basically, it's the same theory. Okay, but because we are doing the robotic control, so it's more on this different topic on translational transformation and also the rotation. Okay, so let's see. Let me show you the transformation. Okay, sorry, today my computer really is a little bit old, so I waste too much time for it. So
Okay.
transformation. Okay. We are talking about mathematical transformation. Okay, so mathematical transformation is a few terms you can look at. Come at me. There are different transformation that including right here. Let's see. Maybe this one is a good. It's a reflection rotation. Okay, it's a different reflection rotation and translation. So let's look at this one. Tutor.com. Okay, this one. The transformation including the dilation. Okay, this one is the making smaller version of the pre-image, shrinking or enlarge. So basically, this one is making the image bigger or smaller. Okay, reflection, rotation, shear is actually tilting. Okay, and but this one doesn't happen on robotic modeling. Reflection doesn't. Okay, this one dilation also no. Okay, these three actually usually happen on game design. Okay, our main purpose is on the rotation and translation. Okay, but because I want to look at talk about the transformation, so I want to show you this page. Okay, how this different kind of the transformation. Okay, and they all be possible by for modeling by math. Okay, but let me put this link to check. Okay, it's very important before we go into the for the robot. You must know about what is transformation. Okay, a linear algebra is for linear transformation. Okay, you use metric to transform some vector from one domain to the other. So that actually is the transformation, linear transformation. But some are not linear transformation, such as this is shear. Shear is not linear transformation. Its transformation will tilt the object. And we don't use it because our robot usually is rigid body. Okay, rigid body means that your shape won't change. Okay, so usually it's translation or rotation. Okay, and the things that you original is called pre-image, and then everything else after rotation is called after image. Okay, so here the same before the translation. Translation means a movement. Before your movement, it's called pre-image. After it's called after image. Okay, and then okay, flip-flop is the same. There's a reflection. Okay, okay, whatever. These are different kind of translation. Now let's look at the translation only. Okay, so translation only. Let's look at one-dimensional translation. Okay, before we go to the two-dimensional or three-dimensional, let's look at one dimension. So one dimension, you have a number line. Okay, you have a car, for example. Let's assume that right now you are at this one called 0. And you move by, okay, here. So you go to X. Okay. So if your car is right here and you go to the X location and you look around. So here, right here, there may be let's assume that here we have a flag at the location 1, right? With respect to 0, is location 1. But your car move. That means that your observation frame move, right? Your observation frame move, and you look back to here. In this system 1, this one is at this frame is located in the 1. But this one, you move to here by X. So under the new system, this spread should be at the where? Minus X plus 1, right? If this one is a new friends 0. Is that okay?
Yes, doc.
Is that okay? So this one
Yes.
actually, why this is important? Because our robot keep moving. So our robot have many actually rotor or joint. Okay, we call it joint. So we talk about every different kind of joint, or rotary joint, prismatic joint, different kind of joint. So each joint will form a observation frame. Each joint will form an observation point. So your joint number 1 move, your joint number 2 will already move to somewhere. Okay, joint number 3. Okay, but you have to, with respect to each joint, there will be one observation frame SYG associated with it. Okay, but before we jump to the 3D frame change, let's look at 1D. 1D actually is something like this. Okay, you actually move by X, your car move by X, and your observation frame move by X. Then your point, okay, it's actually from 1 move to minus X plus 1. But that's because you are using the green observation frame. Okay, the car move forward just like your flag move backward. Okay, it's a similar thing. Is that okay?
Okay, doc.
Your car move forward is similar to your observation frame move backward. So let's look at this mess one more time. So let's assume that our original XY is right here, X axis. Okay, this is axis. This is non-number. This is X axis. So your original observation frame is right here. Your flag is right here, located is number 1 location. Okay, now your frame move to right here. This is new frame. Let's assume this motion is M. You move to M, right? So this one, let's assume we originally have a point right here. It's called X. Okay, it's called X. So original X, this one is X, right? And let's assume that we have a new coordinate, green coordinate. Let's assume it's called big X. Okay, big X. So let's look at the big X and small x. Okay. So basically, big X, green X, okay, will be equal to the small x and minus m. Okay, that's the relationship. Okay. You originally look at here is x, but you look at this one, it actually is this. Okay. Is that okay? So your big X plus m will be your small x. Okay, that's the relationship. Okay, so this is one-dimensional translation. We end up with this. Okay, that's actually good. Let's clean it. Let's look at two-dimensional movement. So we need to model two-dimensional movement. So let's assume the original frame is right here. It's called 0, 0. Okay. Now you actually go to a new frame. Let's assume it's located at the so-called MN point. Okay. And then we do have a point right here. It's called XY. We are trying to solve the big X, big Y. Okay. With respect to the MN. Okay, so we should, this one right here, it should be big X, big Y with respect to the MN, right? Okay, so basically this is how to solve it. You do have a big X. Okay, big X, the relationship with this small x. So small x, okay, it's a big X, big Y. Okay, so your original point move from x 0 to mn, right? So basically you have the big X and big Y. Okay, uh, big X. Okay, okay. Let's see. This point actually is mn. Okay, so let's see. Your big X and big Y. So that's a solution is new coordinate in the xy is a big original big the coordinate in the new frame, right? So this point actually does not move. Okay. So your x minus m will be your big X. Your y, okay, equals y minus n. Okay, so your original small x is big X plus m. Y would be big Y plus n. Okay.
Yes.
Okay, so basically your xy can be written down as the big X, big Y plus a vector of mn.
Yes.
Okay. Or your xy is actually
xy minus mn.
it equals xy minus mn. Okay, this one because your frame move. Okay, your frame move, and then this is how you calculate the vector. Okay, so that can be formulated by the vectors. Now let's actually think about another scenario. We do have a frame, right? But this time frame no change. Let's assume here we originally have a car right here. It's located as small x, small y. And this car moved a transition to a new location that's called mn by the vector. That's a vector that you would add on. So the new location right here should be x plus m, y plus n, right? That's assuming it's a new coordinate in the same observation frame. So your xy, okay, plus mn will be your new xy.
Capital X, yeah.
So what I want to say right here is like, okay, your car movement by mn is the same as your observation frame move backward by minus m minus n. Okay? Is okay? If we do observation on here, the mathematically these two are actually equivalent. Okay?
Yeah.
Okay. So that's actually linear translation. So linear translation, you use a vector addition, subtraction would be good enough. Okay, that would be good enough. Okay, let's look at the rotation. Okay, let's look at the rotation. Rotation will be more difficult. Okay, so let me bring up the slices. Let me talk about rotation one more time. Okay, and rotation probably is the most difficult part. If you can make rotation, you pretty much this course you are okay. You should be okay for everything. So I have a lot of lab, right? I have a lot of lab. Some of them actually show you how these mathematical things can be done. Okay, let me see. Let me choose a different slices. So let's see as module rotational metric. Let's look at it as a rotational metric.
Rotational
Okay.
metric. Yeah.
So rotational metric basically used when your observation frame change or your object move. Okay, either way that you will need to use a rotation. So before we work on the three-dimensional things, let's look at these two-dimensional things. Okay, so these are two-dimensional observation. Let me look at review the trigonometry or the vector one more time. Okay, let's review this one more time. So you do have a coordinate that's called xy. Okay, and from here. So there's a point called xy. And another way to look at it is that here you have something called theta. You have a r. R is the length of this vector, right? So your xy can be written down in another way is that s equal to, I'm sorry, not x1, x. Oh, sorry. S equal to r cosine theta. Y equal to r sine theta. Okay, this is y, this is x. Any questions about it? If we look at the data in the complex domain, this one is real image, real axis. This one is imaginary axis, right? Then we can also write this one as x plus I, y, right? If we look at it as a complex number. So this complex number can also be written down as r cosine theta plus I sine theta. By the Euler's formula, you can write this complex number as E equals R EI theta. Any questions so far?
No, it's okay.
Okay, this one okay. This one okay.
Yeah, it's okay.
That's actually the key point I want to say. Okay.
Yes, right.
I'm going to teach you a easier way
Yeah.
to do rotation.
Yeah, we are adding trigonometry also here, I guess.
Yeah. So we are going to use this one for rotation. Let's assume we originally point is right here. This one is R EI theta. Okay, so basically this angle is theta. We rotate by an angle called phi. So what is this new location? What's the coordinate of that point? If this point rotate by a additional angle of phi. Using vector, it would waste a lot of time. In a complex system, it's extremely simple. You just add the angle to it. That's it. Does that make sense? So basically, it is equal to REI theta times EI phi. So this is the rotational complex number. Okay, that's it. So if we actually write it down in xy, it will be r cosine theta plus phi, r sine theta plus phi. This will be your new x and y. Does that make sense?
Yes, doctor, understand.
Okay. That's what I want to derive the rotation quickly for you. Okay. So we
Okay.
do get the R equals X equals R cos theta times phi R sine whatever. Okay. That's actually erase it. Okay. We don't need this. We just need to have these X, Y things. Okay. So we do have a X equals R cosine theta plus phi after rotation. Y equals R sine theta plus phi after rotation. So X will be equals R cosine theta cosine phi minus sine theta times sine phi. Y will be R sine theta cosine phi plus sine phi cosine theta. Okay? And then put the R into it, right? So R cosine theta, X will be your R cosine theta. So that's assuming X, Y is new X, new Y. So big X, big Y. These are new, okay? These are new locations. So this is big X, big Y. Big X, big Y would be R cosine theta is the original X times cosine theta, cosine phi. And this one minus Y sine phi. Okay? And then this X times sine theta is Y cosine phi plus R cosine theta. That would be, this one would be X times sine phi. Does that make sense?
Yes.
And this one should be able to give you the formation for the matrix.
Yeah.
Because it becomes in cosine minus sine, and then sine, and then cosine times the original xy. Right? I'm using C for cosine, minus S for sine, sine, cosine, and time xy. Okay? So this one give you a relationship of, let me clean it. Let's write it one more time, okay? So basically, that's
Okay.
simple. Let me write it one more time. Your big X will be equal to your R cosine theta cosine phi minus R sine theta sine phi. Okay, your big Y will be equal to R sine theta cosine phi plus R cosine theta sine phi. Right? So your X and Y as a vector equal to okay, this one is X, this one is Y, this one is Y, this one is X. Okay, so it's actually cosine theta minus sine phi. Cosine phi is minus sine phi. And then this one is sine phi, cosine phi. So this thing we call it rotational metric. Okay. And this rotational metric tell you from this point that actually theta xy rotate by an angle of phi you go to a new location that's called XY. Okay, we prove by complex number and also trigonometry theory. This is the easier way to understand it. Okay. Any questions so far?
No, Doc. It's okay. I got it.
Okay.
Yeah,
I wait for you to reply because I want to make sure everyone know it. Okay. One more thing. Okay. One more thing you need to know about is let's assume that we have original frame is XY. You do have a point over here. That's called XY. A small x, small y, right? The previous one is what? Our object move. Okay. Our object move. So you actually times the rotational metric C phi. Okay. Let me use R phi as a rotational metric phi. You times the rotational metric phi, you get a new XY. Okay. But this time, let's assume that it is not the object move. It is the observation frame move. So you have a new observation XY. So originally you have a theta right here. You have your own theta, your object's own theta right here. And then your observation frame move by angle phi. Okay. So now the new angle right here becomes theta minus phi. So what I want to say is that this new coordinate, according to the new frame, green frame, you rotate, your frame rotate by phi. It is similar to the object backward rotate by minus phi angle. So you time the rotational metric minus phi. You should get your new coordinate. Is that okay so far?
Yeah, so far good.
So basically, whatever theory we talk about so far is to introduce you to the translational metric and the translational movement and also the rotational movement for the metric. Okay. So one thing is that you must know about now. Is that the change of the coordinate or is that the change of the object? Change of the coordinate and the change of the object, the mass is similar, but the angle would be just the opposite. You know what I'm saying? Is that okay? The mass
Yes, Doc.
is similar, just the angle is opposite. So if you have that kind of understanding, it will help you to understand this better. So two-dimensional, there are a lot of math. You can look at this.
Yeah, wow, it's good.
Yeah, this
Yeah.
whole thing you can download from the lab. Okay, we have the extra. So 3-dimension, you will have an XYZ. So you will need to deal with the XYZ. Okay. So before we go to the 3-dimension, you have the rotation as well. Before the rotation, there's another one called orientation metric. Okay, orientation metric. So what is the orientation metric? The orientation metric is like, okay, let me show you by hand. Okay. Let me show you by hand. Let me stop sharing. Okay. So let me highlight my own. Let me choose this one. I'm sorry. Let me highlight. Okay. So you see my hand, right? So orientation means that you have a hand, but your coordinate are in the in the 3D space, it's not always this, not always XYZ. It may move like this, okay? So basically, orientation is that even though your source point is the same on 3 dimensions, your origin point is the same, but your dimension or coordinate can be different, okay? So that means that before you discussing the rotation, your original observation frame may have the XYZ like this, right? But actually, your another observation frame may be using XYZ like this, okay, whatever. Then you need to know about this is the difference of the orientation. And then we do have a metric theory to deal with the orientation as well. So that's what is shown right here, this orientation part. So this is slice rotational metric is very important. Okay, so this one you do have an orientation. So let's look at these two orientation. Okay, so your original coordinate XYZ, black one, and the relationship of the new orientation XYZ here. Okay, it's just your X1 is over here. They are overlap. Okay, they are overlap. Z is this direction. Okay, Z1 this direction. Y1 this direction. Okay, everything else the same, except that your XYZ can be observed by the black frame or the red frame. Okay, so let's look at this one. So your XYZ, you do this multiplication. So basically, you have a minus Z. Minus Z equals X1. You see, minus Z equals X1. So red Z, right? Red Z, here you have a minus Z, actually, this one. Your minus Z will be your red X1, okay?
Yeah.
Okay, that's how you build up the relational frame, okay? So this one, your X and Y's relationship, okay? Y1 is actually
Y1 is
Y1 is your X.
Yeah.
Y1 is your X. Okay, this actually, I think it's opposite. Okay, but you can find out the relationship. Is that okay?
Yeah, it's true.
So basically, this is how you find out the orientation metric. So when you deal with a 3-dimensional metric, you need to first set up the right orientation metric, and then add the rotational metric on top of it. Okay. So these are theta, okay, because I don't know, somehow these question mark are all theta. Somehow every time I put it there,
Yeah, got it.
the PowerPoint would actually change it to question mark. Cannot find symbol or something. But anyway, this RG is a rotational metric on Z diagonal. So Z keep the same as Y do rotation. So let's assume we have the X, Y, and Z. Okay. So you rotate on Z. So Z keep the same. And then XY do rotation. Okay, so this XY do rotation. So on the rotation on Z, you actually, this is the rotational metric of the angle phi. If this rotation is angle phi right here. Is that okay?
Okay, doctor.
Okay. So these are
Yes.
Y, these are X. Okay. So basically,
Yes.
3-dimension, you basically use this 3 rotation. Okay. And and when we talk about a object, there are 6 degrees of freedom, right? 6 degrees of freedom. You have an airplane, right, like this. whatever airplane. Okay. So you have the X, Y, and the Z. Okay, 3-dimension that is translational. There are also 3 rotation. That is this one is G. So there's a RG rotation. Okay, RX rotation, and RY rotation. So this is the so-called 3-dimensional degree of freedom on an object. Okay, so these 3 are called pitch, roll, and the yaw. Okay, let's look at the internet. So that's the object. You do have a 3 XYZ transition, and in addition to that, you do have the so-called pitch, roll, and yaw. Okay, that's a 3-dimension. So when you model a robot, you also not only the XYZ, you also have the airplanes, the pitch, roll, and yaw. Okay.
Doc, I have a question here.
Yes,
Can
go
I?
ahead. Go
Doc,
ahead.
like it's like we are using robotics in aviation technology as well, Doc. It's like
Yeah,
that.
yeah.
Okay, thank you. Yeah, like
Yeah.
trigonometry we use like every time. Paramedics.
Sometimes you, some of you join us late, okay? But this whatever math we talk about apply to game theory, virtual reality, okay?
Yeah, it's also yes, Doc.
Augmented reality, and then
Yeah.
also the drone, autopiloting, the aviation,
Yes, Doc.
science, and now this one is robotics. The maths are the same set of maths, okay? The same set of maths are used. So here I'm trying to give you I don't go over the whole course, okay? But I teach you in this extra session just to teach you the motivation, okay? Why we are doing this kind of metric, okay? So this is the rotation and translation. Now let's look at another one, okay? Displacement vector. So I try to give you what is the moral story on this whole thing, okay? I don't repeat the whole video. You can watch the video we have. But the key point is that you must understand what you are doing. So that's the most important part, the moral story. Next one is displacement. So displacement, we do have a rotational metric. So whatever rotation you can do, okay? And then we do have the displacement. Displacement is, we first introduced this when we get started today, okay? So basically that can be done by addition of metric, okay? Addition of vectors. Okay, that can be done by addition of vectors. So one vector adding another vector, transitional vector, you get a new location. So that's the reason we do have X, Y on the same point. Our frame move by A and 0. So this one show you when the frame move by A and 0, your new and old coordinates relationship. Okay, you move your frame to the right, meaning that your coordinate is more or less like have a minus A. You move your coordinate to the right. So right here, this is A from here to here. This is A difference. But this point is the same point. Okay, original called XY. New coordinate using the new frame called big X, big Y. So this is big X, big Y, and small x, small y's relationship. Is that okay? So rotation is just like you multiply a rotational metric. Translation is just like you add in a displacement vector. So these two combination have the combination would give you the complete number system that used in the rotation and translation. And rotation and translation is the most important movement in robot if the body is rigid. Okay, if the body is rigid. So anyway, we finish this one, displacement vector. Now next one, let's look at another one called homogeneous transformation. So this homogeneous translation is using a mathematical technique to combine, okay, I say combine both the rotational metric and the additional translation. So let's look at this one, okay. We do have an original XY location, that's 2D. Let's add another 1 to there, okay. And later you will know about why we adding this 1 would be helping. So this is purely mathematical operation, okay, mathematical arrangement, okay, nothing to do with physics. You add one more dimension with 1, okay. So when you do scale, you do scale. Scale means that your XY enlarge or become smaller, okay. This doesn't happen on robot, but let's assume that you do have a scale. You scale up, your original scenes become bigger, okay, you scale or shrink it. So your XY, your scale metric is like this. And then if you do rotation, then your rotational metric is like this. We talked about it already. This is R theta. Okay, and this R theta happened on the XY domain. Okay, G doesn't rotate. G actually right now is fixed as 1, so G just pick 1. Okay, so this is a 2-dimensional operation, but we add 1 more dimension to it. But you will have a rotational metric like this. Translation, you will have 1, 0, 1, 1. Okay, like this, and you do put the translation on X and Y on here. Okay, so what's this for? This one just tell you that if you have a whole combination of everything, rotate, translate, and the scale, you can put a scale metric times the rotational metric times the translation metric times your original vector XY and 1 more dimension with 1. This will give you the new combination of X prime, Y prime, and 1. That's called homogeneous. Homogeneous is the same kind. We convert the vector, displacement vector, rotational metric, scaling metric in one same format. That's called homogeneous transformation. Homogeneous means of the same kind, right? Heterogeneous means of different kind. Does that make sense? Any questions so far?
No, doc. We are good.
So basically right here, I try to teach you just the key idea, okay? I don't go over the whole chapter. It's actually a lot of time. You can watch the video, okay? But the key idea right here is that you set up 3 kind of matrix combining together that will give you the complete motion transformation. And scale doesn't happen on robot, okay? Robot doesn't become bigger or smaller, okay? But anyway, we put it together over here, okay? And then this will show you the application of this, okay? You do everything together. Okay, so we combine the displacement metric and the rotational metric, you become something like this. Mathematically, it's doing this calculation. Okay, but you actually using metric to do this. Okay, that's why the first chapter we do have that linear algebra, wanting you to operate on the using Python to operate on the vector and also the matrix. That's because all of the motion in robot can be modeled by matrix. Okay. And you are dealing vector and matrix all the time this course. Is that okay?
Okay, Doc.
And HTM, homogeneous transform matrix, is to combine everything you originally calculated separately into one matrix using the multiplication of 3. Okay. And during your multiplication, you also need to put the so-called orientation matrix into it. Okay. We talked about it previously. So this one just to show you how these things got combined. Okay. Okay, so this portion just to show you how things are combined. Whatever, okay. And you need to work on right now, chapter 2, okay. You will need to work on this up to here, okay. Any questions so far?
Oh, it's okay.
So this, you will find that there are 2 sets of the PowerPoint, okay. So this blue set, light blue set, this one originally I designed it for a undergraduate level of the robot. Okay, so it's more like intuitive, more I would say simpler. Okay, but go into the detail more. The other set is for master level. Okay, when I design the slices, this one is more mathematical, more theoretical, and kind of not easy to understand. Okay. So when you study, I suggest you go to the course shell. Okay. Go to the course shell. So each week we do have the video that I recorded. Okay. Those video actually is in the lecture. So in the lecture, I'm teaching the master levels course. Okay. And then you can see that there's always a lab session. And this lab session, I'm using that undergraduate package to teach you. Okay. So in a way, if you don't know some basic idea, you should go to the lab instead of just the lecture. Lecture is more difficult. I would say harder to understand. And the lab usually give you what is kinematic diagram, how we do it. Okay. So this portion is easier and more intuitive. Is that okay?
Okay, Doc. Okay, Doctor.
Yes, makes sense.
Okay, so roughly I finished whatever I want to say today. Okay. This is week 2, so we finished this robot arm, rotational metric, displacement, right? We finished this. Any question?
No, Doc.
Next one will be week 3, okay? But today we just cover up to week 2, okay?
Okay.
Okay, if no question, we are up to here today. Is that okay?
Okay.
Yes, Doc. A small question.
Yes, question. Yes, go ahead.
Yeah, this is Shabnam Kalim. I just mail you also regarding the final project. So is it necessary to make a hardware robot?
No. We have 3 projects. I talked about it last week.
You told me, but I had
you can
just
choose to work on a robot. That's actually welcome. But if you don't have budget or for some reason you just work on mathematical modeling, I'm fine.
Yeah. Okay. And I will try.
Okay. And also
all the simulation code and everything.
If you are not really that good in programming and math, you choose to work on another one that's idea exploration. So trying to come up with a new idea for robotics, that's also okay. That's a paper study and idea project. So either way, okay, anything related to robot is okay, but don't give me a project on machine learning, okay? Machine learning.
No, I won't. Okay,
it's different topic, okay? Some students give me AI or machine learning. That's totally a different topic, okay?
No, I'll give only on our subject,
Yeah,
like
only
robotics.
our course is teaching robotics, okay? Even though sometimes I talk about AI and machine learning, but our course still remain on robotics, okay? Only robotics project will be acceptable, okay?
Okay, Doc. Thank you so much. I
But
appreciate it.
it is a creative art project, so you can try whatever you want to do as long as it's within the domain of the robotics.
Okay, Doc. Thank you so much. Thank you.
So no limit on what you can do, okay? You just be creative to plan it. And third week, we will need you to submit a proposal, okay? What you want to do, okay?
Yes, Doc. Okay, thank you.
Okay, other question?
I have no questions. I will try to watch again all these
Yeah.
videos.
So
Thank you.
Monday meeting, I don't want to make it too long, okay? Because everybody are
Yes.
busy. So basically, we'll go over the key concept and also answer whatever question you have in homework and project. Yeah, any question? No?
No.
Okay.
Sorry.
Yes. Any question?
No. For me, it's okay.
Okay. Good. Okay. And always one more thing. Okay. You can still always send me email to my Louis account. Okay. Or my personal email also accepted. Or if you like, you want to send me to Facebook. Okay. You can also send me to my Facebook site. Okay. My Facebook site is facebook.com, okay, and then Dr. Eric Chow, okay. This one, if you find my page, actually it look like teaching some computer for high school student. Yes, I do. I do teach. I do coach student in high school for user competition. Okay, USA Computing Olympia, and I also have a student. I teach them AP course and AP Computer Science A, AP Computer Science Principle. And over the past few years, I do send a few students to MIT, Harvard, and whatever program, Harvard and Stanford. Okay. So I do work with them. I'm not doing advertisement, just let you know, don't surprise that I do have some kind of activity like that. Okay. Okay, so that's, if you want to reach me, you can send to me this one, become a friend, okay, facebook.com/Dr. Eric Chow. Okay, that's my ID in Facebook. And this will be faster than sending email, okay, because I'm every day tons of the messages coming in. I would say more than 20 of them every day, okay? I deal them every time, okay? I try to reply you within a day. Okay. This Facebook, I can guarantee you, I'll reply you within a day. Okay. If I find time and I read it, I will reply. Email, I don't know because I'm not full time with Louis. So sometimes the email, I may have 2 days or 3 days. When I look at the homework, I will check the email. Okay. So maybe a little bit slower. So if you want to reach me faster, the Facebook Messenger is actually better. Okay. Any other question?
No, Doc. Really.
Okay. So let me know if there are questions. Okay. Sometimes if the question got too hard, I may zoom you. Okay. But depends on how hard it is. Okay. Okay. No question. Then that's it for today. Okay. Thank you. But feel sorry for today. My computer start for half an hour. Okay. So I'm starting a little bit late. Okay. Sorry for that. Okay. See you next time. Bye-bye.
Thank you so much. Thank you.
Bye-bye.
Bye. Thank you.